Welcome to Mr. Math Academy. Grow your math brain.
Hello friends, welcome back to Mr. Math Academy. So here in this video we solve one numerical which is based on the generalized Hooke's law. So already we have discussed what is the Hooke's law, what are the basic concept about the Hooke's law, and what are the generalized Hooke's law when we go for the three-dimensional stress state element here. Okay, now let us go for one numerical which is based on the generalized Hooke's law here. Now we will go for the what is the numerical here. So he has given somewhat the on the rectangular plate he has given. So again he has given some of the dimensions over here. So he has given a steel plate of 1 meter long. So he has given the 1 meter long steel plate. So 0.4 meter wide. So this will be the wide, that is the dimensions he has given. So again he has given the 20 mm of the thickness of this material is given. Again the later thing is, so he has given the what is the stresses sigma x and sigma y. So these two are the unknown parameters. So but the condition is what he has given, the sigma x and sigma y will be acting along the length as well as along the width here. So but he has not given what will be the one more stress, that is the sigma z if I take. So it will be along with the thickness here. So he has not given that one. So since it is a biaxial member. Okay. Now if the increase in length is 0.6 mm. So if the increase in length is means what? So when we apply some load here, there will be a stress in the longitudinal direction. So in that case, because of that applied load here, so there will be a deformation takes place. So the deformation, that's nothing but a change in length. So in x direction is a 0.6 mm he has given. Again increase in width is 0.09 mm. Means what? Because of the sigma y, okay, because of the sigma y there will be an increase in the width of 0.09 mm here. So again what we have to find out, okay, it's a simple thing here. So what he has given is, so we need to find out what will be the sigma x and the sigma y. So he has not given the sigma x and the sigma y, but the thing is that sigma x and sigma y he has given in which direction it will be acting here. So means what, in x direction as well as in the y direction. So second thing is what we have to find out, the change in thickness. So what happens when we apply some load, okay, because of the it will be creates in the stress in the member. So in x direction as well as in the y direction. At the same time what happens, so the length will be increases, the width will also be increases, the thickness will be decreases here because of the change in dimensions along the x axis and the y axis here, that is along the length and the width here. So means what, at the end the thickness will be gets reduced here. So I need to find out what will be the change in thickness. The last one, I need to find out what will be the change in volume in the plate here. So obviously when we apply some load, okay, obviously there will be a change in dimensions. So like delta Lx, delta Ly, delta Lz in all the three axes. So at the end I need to find out what will be the change in volume, that is the delta V I have to find out. Okay. Now let us move on to the how to solve this kind of problem. So he has given the Young's modulus of the material 200 gigapascal as well as the Poisson's ratio. Now let us first we will write what is the data he has given the problem. Okay. So he has given that. We will try to write the what he has given in this problem. So the data is, so he has given the length and the width here. So in the x direction, if suppose if I am taking this is the x axis, so this is the, so say since it is acting in this direction, okay, I will try to take, so this is y and this is my z axis here, okay, so x, y and z axis here. So in x direction I will consider this is the length. So in the y direction I will consider the width here, that is the 0.4 meter, but in the z direction I will consider it's a thickness here. So I have to find out, so because he has given the data means, so I just take, so before that, so he has given the 1 meter length. So 1 meter length means the length in x direction, so it's a 1 meter, so that is equal to, I will take 1000 mm, okay, for simplification. So again he has given the width here, so this is the width. For simplification purpose, for simple to understand, so I will just represent all the terms here L, but I will represent with the axis here so that we can easily understand here. So this width I will represent with the L, but the thing is I will represent with the, okay, with the help of this y axis. So I will take length in the y direction, that is the width is equal to 0.4 meter, that is a, I will take in terms of mm, so it becomes a 400 mm. Okay. So next thing is what he has given the 20 mm. So 20 mm means it's a thickness. So if I take this is in a z direction, I will take this is a Lz is equal to, actually this is the thickness here, okay. So don't consider this is the length is same, okay. If you are getting confusion, you can represent with the width, that is a b, and the thickness t, okay. It's left to, it's a simple thing. So for understanding purpose, so it's a directly 20 mm here, okay. What else he has given? He has given the Poisson's ratio. So I'll represent with the nu here, it's a 0.25, and Young's modulus is 200 gigapascal. So I'll take in terms of megapascal or Newton per mm square, it becomes 200 into 10 power 3. So it's a megapascal or it's a Newton per mm square, okay. Now what we have to find out? So I'll just write here to find. So I'll just take the first one, so sigma x and the sigma y, that is the direct stresses or normal stresses in the x axis and the y axis. So sigma x and the sigma y. Second thing, I have to find out the change in thickness. So change in thickness means I'll represent with the change in means what? I'll represent with the delta. So here delta L with the z direction. So z direction means it represents the thickness of the plate here, okay. So the third one, I have to find out the change in volume. Change in volume is it's a delta V of a member, okay. So these three things are we have to find out here. So how to find out this kind of problems? Okay, let us go for the solution here. So very first thing is what? So since this problem is related to the generalized Hooke's law, so we just write some few equations which are related to the generalized Hooke's law, okay. We know that the generalized Hooke's law is given by what? So I can take epsilon x is equal to, okay. So epsilon x is equal to, so already we have studied these equations. So you can, for understanding purpose, you just write sigma x by E, sigma y by E, so sigma z by E, okay. Now when you are taking the strain in the x direction, so the first, that is a sigma x by E, you can take it as a positive, okay. But the thing is in the y and z direction, so it will be a negative here with, we have to take the Poisson's ratio. So only these two changes we have to take. Similarly, if I write for the y direction, that is the strain in y direction is given by, first thing is what? I'll write sigma x by E, okay, sigma y by E, sigma z by E. So just for understanding purpose, so that easily we can remember here. So since it's a epsilon V, I'll just take in place of sigma y, I'll positive. In other two cases, in other two terms, I have to take with the minus with new value. So this becomes minus nu, so this becomes with minus nu, okay. So we can write with the epsilon z also. So this becomes, I'll write sigma x by E, sigma y by E, so this is sigma z by E. So since it's along with the z axis, I'll just take positive here, but in other two terms I'll just take with the negative nu, that is the Poisson's ratio. So these three equations are called as a generalized Hooke's law, okay. So these equations will be helps to solve, so some of the terms over here. Now again, so epsilon x is nothing but what? It's a strain in x axis here. So this equation epsilon x, I can also write it as a, so it is a delta L x by length in the x direction. So because this is a generalized Hooke's law, but the basic thing is what? Strain is nothing but change in length by original length in the x direction, since it is a x direction. So similarly for this case, I'll write it's a change in length in y direction, length of y direction. So length of the y direction, it indicates this part, that is in the width here. So epsilon z means it's a strain in a z direction, so that gives the information regarding the thickness of the material here, okay. I'll just take here delta Lz by length of the z, okay. So these three equations we need to remember here, these are the generalized Hooke's law, okay. Let us consider, so what we have to find out? We need to find out the sigma x and sigma y, okay. If you just take here, we can easily solve this problem, okay. Here what he has, since it's a two dimensional, that is a biaxial here, only has given Lx and Ly is given. So again sigma z becomes 0, because he has not given the sigma z, since it's a biaxial, he has not given, means obviously it will be a 0 since it's a biaxial, Okay, now let us will go for this condition here. I'll just take this equation. So this becomes delta Lx by Lx is equal to sigma x by E minus nu sigma y by E. Okay, so I have not taken this nu into sigma z by E. So because since it becomes a 0 here, so why it is 0 means since it is a biaxial, so he has not given in the problem, that will be a 0. I will not take that equation for this case now because it will become a 0. Okay, now let us try to substitute the values here. So delta Lx is nothing but what? It is a change in length in the x direction. So what he has given, so this 0.6 mm. Okay, so this delta Lx is equal to what? The increase in length is 0.6 mm and increase in width is 0.09 mm. So this delta Lx is equal to, actually this is a 0.6 mm and again delta Ly is equal to 0.09 mm. These are the two, again some data he has given. So we'll just simplify this, we'll just substitute the values here. So delta Lx is equal to 0.6. Length of the x means length in the x direction is what? It's a 1000 mm. Okay, it's a 1 meter. I'll just take in terms of mm. So sigma x is unknown. So Young's modulus is, since the Young's modulus is same, I can take the common here. So it becomes 200 into 10 power 3. So here it is a sigma x will be remains minus nu is a 0.25, that is a Poisson's ratio, sigma y. Okay. Now if I just simplify this, I can get a equation 1. So that becomes sigma x minus 0.25 sigma y is equal to, so when we just cross multiply, if we simplify, what I am getting the equation here is, so it is a sigma x minus 0.25 sigma y into 120. Okay, I will just take this is the equation 1. If you just cross multiply this 210 power 3 here, okay, so I am getting a 120 here, that I will take the equation 1. Okay, for time being I will just remove this part here. Okay, I think we no need to write the equation, that is a problem also here. Now I will consider the equation 2 here. So what is given in the equation, sorry, if this is the equation 1, okay, when we are considering the sigma, that is this epsilon x here. Now I will consider this epsilon y, that is in the y direction. So it becomes epsilon y is nothing but delta Ly by Ly here. So this delta Ly by Ly is equal to, so again I will not consider the sigma z value because it is a 0 here. So only what I am getting here is it's a sigma x by E with minus nu, and again this is a plus sigma y by E. Okay, the third part will be 0. Okay, now delta Ly means it's a change in length in the y direction, it's nothing but the change in width here, it's a 0.09 mm, and the length of the y, that is the width of the member, is it's a 0.4 meter, it's nothing but a 400 mm. So that is equal to, so minus of 0.25 sigma x, okay, divided by Young's modulus is there. Okay, I'll just take the common right here itself. So it becomes 1 over 200 into 10 power 3. So it's a minus 0.25 sigma x plus sigma y. Okay. Now again if you just cross multiply here, so we are getting the equation as 2. So there is minus 0.25 sigma x plus sigma y, that is equal to, so around 80 I am getting here, sigma y minus 0.25 sigma x is equal to 45. Okay, so this is the equation 2. Now we have got the two simultaneous equation, that is the equation 1 and equation 2. We just simplify this. Okay, we just solve these two simultaneous equation. Solve equation 1 and 2. So we get sigma x minus 0.25 sigma y is equal to 120, and again this equation 0.25 sigma x plus sigma y, that is equal to 45. Okay. Now if you just solve this equation, that is a simultaneous equation, we are getting the sigma x is equal to some 180, it's around, I am getting a sigma x is equal to 140 megapascal, and sigma y is equal to, so I am getting 80 megapascal. So this is the first part what we have got the value. So sigma x is equal to 140 and sigma y is equal to 80 megapascal. So okay, so this is the first part. Okay, now let us move on to the what is the delta z here, that is a change in thickness of the material. Okay, so what is the change in thickness of the material means? So we have already used these two equations. So to calculate this delta Lz, to calculate the second equation delta Lz, that is a change in length in the z direction, or it's a change in thickness of the member. So I will consider the equation 3 here, that is the third equation. So this becomes, to calculate the second one, delta Lz is equal to length of the z, that is nothing but we have to take the thickness. Lz is nothing but it's a length in the z direction, it indicates the thickness of the member. So this becomes minus nu into x by e, again this is minus nu into sigma y by e, because sigma z is 0 always for this problem. Now already we have calculated the sigma x is equal to 140 megapascal and sigma y is equal to that is 80 megapascal. Okay, Poisson's ratio is 0.25 and Young's modulus is 200 into 10 power 3. So this Lz is nothing but it's a thickness of the member, that is at 20 mm. You just simplify, okay, we will be getting the delta Lz, it's nothing but a change in thickness of the member. So delta Lz is equal to, this is at 20 mm minus 0.25, so delta Lx is 140, so this is 200 into 10 power 3, you can take here. Okay, I will just remove this part also. So this is minus 0.25 into sigma y is 80. So again 200 into 10 power 3 will take. Now you just simplify this equation by cross multiplying. So I am getting a delta z. This is also called as a change in length, a change in thickness. Therefore, change in thickness, that is delta Lz is equal to, you just simplify this. So we are getting some negative value, since because the longitudinal direction when we apply the load and the y direction we are applying a load means the length has been increased, but the lateral dimensions, that is with respect to the thickness, so there will be a decrease in the thickness. So I have to get a negative value of that. So I am getting around minus 5.5 into 10 power minus 3. So this is a change in thickness here. So this minus indicates actually the decrease in the thickness here. Okay. So this is the second part what we have calculated. Now we need to find out the third part is what. So we have to calculate the change in volume. So we will go for the change in volume here. So change in volume is nothing but what, epsilon v actually. So that is the strain, volumetric strain here. So which is given by delta v by v. So by using the since it's a problem is something like, okay, 3-dimensional case, okay, by using the generalized Hooke's law we need to find out here. So that 3-dimensional generalized Hooke's law, if you just simplify, because we know that epsilon v is equal to epsilon x plus epsilon y plus epsilon z for a rectangular bar cross section, already we have done. Okay, that is a volumetric strain. So in this equation, if I take all these 3 generalized Hooke's law, at the what is the equation what I am getting here is sigma x plus sigma y plus sigma z by e, okay, into 1 minus 2 nu. So this is a volumetric strain for the member here, okay, for a 3-dimensional case. Now in this equation, if I substitute the values, I am going to get what is the change in volume. So this delta sigma z becomes a 0, 0.25 Poisson's ratio Young's modulus we can substitute. The sigma x is equal to 140 megapascal. So sigma y is 80 megapascal. So here the volume we have to find out, because the dimensions she has given in the for a thickness of the plate, for a plate here means we can calculate the volume here. The remaining unknown part is change in volume only. So I'll just calculate here. So delta V by the volume of the plate here is, it's a 1000 mm length is given, 40 mm width is given, and thickness 20 mm given. Okay, that gives totally entire, it's a volume of the plate, that is equal to, so sigma x is 140 megapascal plus this sigma y becomes, it's a 80. Okay, so this sigma z becomes 0 here. Okay, divided by 200 into 10 power 3 into 1 minus 2 into 0.25. Now just simplify this part here. So then what I am getting, the change in volume equation is, so it's a 4400, so it's a 4400 mm cube. So this is a change in volume for a given problem here. I hope you are getting this problem. Okay, it's a very simple thing. What we have to remember here is, so what is the three-dimensional stress state and what are the generalized Hooke's law. Okay, and each and everything, if you just basic thing, it's not a difficult one, it's a very simple thing, easily we can solve and we can get the score here. So that is the change in thickness is minus 0.55 into 10 power minus 3, that will be the contraction takes place. So this will be the change in volume, it's around a 4400 mm cube. So please, if you like this video, please kindly share it with your friends, okay, and comment, and okay, subscribe to our channel.